What is the aurora? Known as the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere, these dazzling light displays are among the most captivating natural phenomena visible from Earth. For students of astronomy, understanding the aurora is not just about appreciating its beauty, it's about uncovering the interplay between the Sun, Earth's magnetic field, and our atmosphere. Let's explore how the aurora forms, the science behind its vibrant colors, and what makes it a critical subject in space and atmospheric studies. The aurora is a luminous display caused by the interaction of charged particles from the Sun with Earth's magnetic field and atmosphere. The process begins with solar activity, such as solar flares or coronal mass ejection (CMS), which release streams of charged particles, primarily electrons and protons, into space. This stream, known as the solar wind, travels millions of kilometers, eventually reaching Earth's magnetic field. The magnetic field acts as a shield, protecting the planet from these high-energy particles, but at the poles, the field lines dip inward, allowing some particles to enter Earth's upper atmosphere. Once these particles enter the atmosphere, they collide with gases like oxygen and nitrogen at altitudes ranging from 80 to 300 kilometers. The energy from these collisions excites the gas molecules, causing them to emit light as they return to their normal energy state. The color of the aurora depends on the type of gas and the altitude of the interaction. For instance, oxygen at high altitudes produces a greenish-yellow glow, the most common aurora color, while oxygen at lower altitudes can create a rare red aurora. Nitrogen, on the other hand, contributes blue or purplish hues, adding to the aurora's vibrant palette. Auroras are closely tied to the Sun's activity cycle, which spans about 11 years. During periods of high solar activity, known as solar maximum, auroras become more frequent and intense, often visible much farther from the poles. These periods offer prime opportunities for studying the aurora's effects on Earth's atmosphere and its implications for technology, such as satellite communication and GPS systems, which can be disrupted by the geomagnetic storms that produce strong auroras. Understanding the aurora also involves delving into Earth's magnetic field, a key topic in astronomy and geophysics. Earth's magnetosphere, shaped by the interaction between the solar wind and our planet's magnetic field, serves as the stage for auroral displays. The aurora occurs primarily in oval-shaped zones around the magnetic poles, called auroral ovals, which shift and expand during geomagnetic storms. Observing these zones provides scientists with valuable data about how the Sun and Earth exchange energy and matter. For indigenous cultures and early explorers, the aurora held deep spiritual and cultural significance, often interpreted as messages from the heavens or manifestations of spirits. Today, auroras continue to inspire awe, but now they also offer a scientific window into the workings of the Sun-Earth system. Studying the aurora helps us understand space weather, a field that examines how solar activity affects not only the Earth but also human technologies like power grids, radio signals, and space travel. Astronomers and atmospheric scientists use a variety of tools to study auroras, including ground-based observatories, satellites, and even sounding rockets launched into auroral regions. Instruments like spectrometers and magnetometers measure the aurora's composition, intensity, and magnetic field interactions, providing insights into the processes that drive it. Missions like NASA's Themis Time History of Events and Macroscale Interactions during substorms have revealed details about how energy is transferred within the magnetosphere to trigger auroras. For those lucky enough to witness the aurora firsthand, the experience is unforgettable. Prime viewing locations include northern latitudes like Norway, Sweden, Finland, Canada, and Alaska, as well as southern regions like Antarctica and parts of New Zealand. The best time to see the aurora is during the equinox months of March and September, when geomagnetic activity is typically at its peak. Clear, dark skies away from city lights offer the ideal conditions for enjoying this celestial spectacle. For students and enthusiasts of astronomy, the aurora is more than just a light show, it's a dynamic display of the interactions between our planet and its star. It embodies the principles of electromagnetism, particle physics, and atmospheric science, making it an excellent case study for understanding the interconnectedness of space and Earth systems. The next time you see a video or photo of the aurora, think about the solar winds that traveled millions of kilometers, the magnetic forces that guided them, and the atmospheric reactions that brought them to life in brilliant color. In conclusion, the aurora is a stunning testament to the power and complexity of the natural world, bridging the gap between astronomy and earth science. It's a reminder that our planet is constantly interacting with its cosmic environment, and it inspires both wonder and scientific curiosity. Whether you're a student eager to understand the science behind it or simply someone captivated by its beauty, the aurora invites us to look up and marvel at the cosmic forces that shape our world.